Ever looked at a building, maybe your school, or that bustling railway station you pass every day and just stopped, truly wondered, how on earth did they do that? Or even maybe, why is this room built just so? It's pretty incredible when you really think about it. Every single space we interact with, from the cozy comfort of your home to the soaring ceilings of a museum, is actually a meticulously designed puzzle. It's the direct result of incredible imagination and teamwork by, well, brilliant minds who first dream up, then meticulously plan, and finally construct the physical world all around us. Today, we're taking a deep dive into the fascinating worlds of architecture and engineering. Yeah, we're going to peel back the layers a bit and show you the hidden secrets behind the spaces you move through every single day. Our mission, to demystify the design and construction of our built environment. We'll use simple day-to-day examples that anyone, maybe especially a curious 8th grader anywhere, even in India, can easily understand and connect with. You're going to discover how every door you open, every window you look out of, and every path you walk down is actually a deliberate choice, made to serve us better, to keep us safe, and to make our lives just a little bit easier and more enjoyable.
And what's truly compelling here, I think, is that the foundational sources for our deep dive today come from a classic, almost encyclopedic guide for architects and engineers. These aren't just dry textbooks, they're really rich with insights. They reveal that designing spaces isn't merely about aesthetics, making things look pretty, but it's fundamentally about a profound understanding of how people live, how they move, and importantly, how they interact within these spaces. It's about solving complex, real-world problems with incredibly clever, often invisible solutions you might never even notice until now. We're going to try and highlight those aha moments for you.
Okay, so if buildings are these intricate puzzles, who are the masterminds behind their creation? Who are these visionaries? The ones who see an empty plot of land and imagine a bustling school or a calming hospital or a welcoming home. Think of them as superheroes, maybe. But instead of capes, they might wear hard hats and carry rolls of drawings. They're special powers, an almost boundless imagination combined with a really sharp, rigorous approach to problem solving. These are our architects and our engineers. But how do they actually begin to turn a dream or a client's need or even just a spark of an idea into a real, solid, functional building? A building that stands tall for decades. Well, it all starts with a language of its own. Imagine for a moment you want to build the most epic Lego castle ever. You probably wouldn't just grab a random pile of bricks and start stacking, hoping for the best, would you? My guess is you'd probably begin with a rough sketch first, maybe on a piece of paper, showing where the main towers go, where the drawbridge will be, how the rooms connect like the Great Hall to the kitchen. Then, if you were really serious about this masterpiece, you might draw a much more detailed plan, showing exactly how many studs wide each wall needs to be and where every tiny window brick goes. Buildings are, well, precisely the same, just on a slightly grander scale.
That's a perfect analogy, actually, because what's truly insightful here is that those very initial plans and diagrams, what architects often call conceptual sketches, are exactly like your rough Lego sketch. They often don't have exact scales at that point. Their main purpose, really at that early stage, is to illustrate the general layout, to express the fundamental relationships between different spaces. So, for example, they show how a living room flows into a kitchen, maybe, or how classrooms are arranged around a central area in a school. Precise measurements, exact dimensions. They aren't crucial just yet. It's all about getting the big picture right first. Understanding the flow, the connections, the overall feel. It's like the blueprint of the idea itself.
That makes perfect sense. Yeah, you have to get the overall vision agreed upon before you zoom into the nitty-gritty details. But okay, once that big picture is clear and everyone's on board with the general layout, then for the actual construction, they need incredibly precise instructions, right? That's where those detailed drawings come in. The ones with all the exact measurements down to the millimeter sometimes. They show everything, the precise width of a doorway, the exact height of a ceiling, the thickness of a wall where every pipe and wire is supposed to run. Think of them as a hyper-detailed, super precise recipe for the construction crew, telling them exactly what ingredients to use, in what quantities, and exactly how to combine them. Without those detailed plans, well, it would be absolute chaos on site, wouldn't it? And probably unsafe buildings, too.
And if we connect this to the bigger picture, it becomes really clear that architects, engineers don't just invent these measurements or guidelines on the fly. It's not purely imagination. They adhere to incredibly strict rule books known as standards. These are developed by organizations like the British Standards Institute, or BSI, and the German Institute for Standardization, DIN. You see these references a lot. These standards are absolutely critical. They ensure buildings are not only safe and functional, but also efficient and consistent, no matter where they're built. They provide specific codes for, well, everything, from how thick a load-bearing wall needs to be, to how big a water pipe should be for a certain flow rate, even to how much natural light a room should get. These aren't just helpful suggestions. They're often fundamental, sometimes legally binding requirements. It's like a universal language of building safety and quality, you know?
So these standards are like the secret code for quality and safety.
Got it. And in today's world, they don't really use those giant drafting tables with paper and pencils anymore, do they? Or not mainly anyway. They use special computer programs, almost like super smart drawing tools.
Exactly. Computer-aided design, or CAD, it's transformed the industry. Imagine drawing different parts of your house, but instead of cramming it all onto one sheet, you use separate, transparent sheets, like digital tracing paper. One sheet just for the walls, another for the furniture layout, a third just for doors and windows, maybe another for plumbing, another for electrical.
Oh, okay.
That's essentially how CAD drawings work. They use what are called layers to keep everything organized and separate. This layered approach is brilliant because it helps them see every part clearly, make changes easily without messing up other parts, and most importantly, identify and fix potential clashes or mistakes like a pipe running through a beam long before they become really expensive problems on the construction site. The precision is remarkable. That layer concept sounds incredibly useful. Avoiding those costly mistakes on site must save a fortune. Okay, here's where things get really interesting, for me anyway, and maybe a little surprising. Did you know architects are kind of secret masters of human psychology? They don't just design structures of steel and concrete, they design experiences for you. For the person who will be living or working or just moving through that space, it's not just about beams and bricks, it's profoundly about feelings, comfort, and, well, the intuitive flow of how we move.
This brings us to a fundamental question, really. Why are things around us the sizes they are? Why is a chair a certain height? Why is a kitchen counter at that level? The underlying principle, as our sources emphasize, is that man is measure and purpose. It's a classic idea. Architects and designers determine appropriate sizes for everything, containers, furniture, how much space a person needs, by deeply understanding the dimensions of the human body, human limbs, how we move. They meticulously account for how much space a person occupies in different postures, sitting, standing, bending, reaching, even, walking through a door carrying shopping bags. They're also intimately familiar with the standard dimensions of everyday appliances, fridges, washing machines, ovens, ensuring they fit seamlessly. The goal is always designing for comfort, safety, utility, but without wasting precious space. It's a delicate, scientifically informed balance.
So the next time you sit comfortably at a dining table or easily open a door without having to squeeze or reach for a cup in your kitchen cabinet, remember that someone, an architect or an engineer, calculated precisely how much space you need to do that without thinking. Like, the sources mention a square dining table for 4 people might be 85 by 85 centimeters, typically. But if you want 6 people to sit comfortably, it stretches to maybe 130 by 80 centimeters. To give everyone enough elbow room, space to move their chairs, an armchair, maybe 70 by 85 centimeters. A couch for the family could be 95 by 195 centimeters. These aren't random numbers, are they? They're based on, real studies of people.
Absolutely. Extensive ergonomic research, studies into human dimension anthropometry, it's called movement patterns, and just what makes a space feel comfortable and efficient for the human body. It's amazing how much thought goes into things that seem so simple, so everyday.
It really is. Now, you mentioned something earlier about our eyes playing tricks. How does that fit in?
Yes. What's especially fascinating is how our eyes can sometimes, deceive us. And brilliant architects know this. They often use it to their advantage. For instance, the source material notes that lines that are actually the exact same length can appear different because of visual cues around them. Think of those classic optical illusions.
Oh yeah, like the arrow lines.
Exactly. Or, more subtly, walls that slant inwards just slightly can actually look perfectly straight to our eyes. This can make a space feel more stable, maybe more grand. Even the way a large window is divided into smaller panes can dramatically change how big or small an entire building seems from the outside. They're constantly thinking about visual perception and how to subtly manipulate our senses to make a space feel a certain way. Spacious, intimate, inviting, grand. It's a bit like visual magic, isn't it?
That's wild. So the world isn't just built around us. It's deliberately designed to make us feel and move in certain ways. It really is like a bit of friendly psychological trickery. Like you mentioned, a narrow corridor making the next room feel bigger.
Precisely. You step out of that constricted hallway into the main room, and bam, that room feels much larger, more expansive, just by contrast. You get that sense of release. It's all about creating subtle cues that influence our perception and comfort as we navigate spaces. It's not just what they build, but how they make us feel in those spaces. That's key.
Okay, so our design superheroes have the big idea. They know how to draw it precisely. They've thought about us, the people using it, even how our eyes work. What happens next? How does this brilliant idea actually transform from drawings and psychological insights into a real, tangible building, one you can walk into, learn in, or call home?
Well, the process usually kicks off with a detailed questionnaire from the client, the person or group who wants the building. But it's not just a simple checklist. An experienced architect takes this initial input, which might be quite broad, and helps translate it into a much more detailed, structured plan. This often begins with what's called a sketch scheme. Here, they start with simple rectangular room shapes drawn to scale. But crucially, these shapes are grouped and arranged not just for looks, but by how they should functionally relate. Kitchen near dining, classroom near library, They even start factoring in external elements right away the direction of the sun, prevailing winds to optimize things like natural light and ventilation. It's where abstract ideas start taking solid form on paper.
That sounds like an exciting puzzle phase. Then comes finding the absolute perfect spot for the building on the land, right? Must be complicated.
Oh, incredibly complex. It's not just finding any empty space. They consider everything. Sunlight passed throughout the day for warmth in winter, shade in summer. Prevailing winds, access roads, the natural contours, hills, valleys, any existing features like beautiful trees they want to keep, even what's around it, the neighborhood context. Imagine trying different spots for your house on a plot of land, like moving puzzle pieces, until you find that perfect fit. Best view, ideal light, most convenient access. It's a huge optimization challenge.
Moving puzzle pieces, I like that. And then there are rules they have to follow too.
Exactly. This iterative process, exploring options, layouts, sites, leads to discussions, weighing pros and cons, until a decision is made, and the image of the future building gradually comes into focus, as the source puts it. But it's not just about what looks good or works best functionally. There are also incredibly strict rules, state building regulations, local land use planning laws. These are primarily focused on public safety, ensuring buildings won't collapse and become fire hazards. But also things like privacy, environmental impact, health and well-being. They dictate setbacks from neighbors, height limits, how much of the land you can cover. They're a fundamental framework for responsible development. You can't just build anything anywhere.
Right. Regulations. Makes sense. And of course, building costs money, often a lot of money. How do they manage that side of things?
The budget. Yes, architects and engineers have a whole precise system for this, often following detailed rules like the German standard DIN 276. This standard provides a meticulous framework to estimate, calculate, and forecast expenses at every stage, from the very first idea through design, construction, even into maintenance. It's like planning a massive, incredibly grand party, maybe, where you have to budget for every single thing, invitations, catering, venue, and track it all the way through.
Making sure you don't run out of cash halfway.
Exactly. It requires incredible financial foresight and discipline to manage projects, especially large ones, from beginning to end. Every cost needs accounting for.
That was a fantastic journey through the designer's mind. So we've got the idea, the drawings, the human element considered. Now let's get our hands dirty, so to speak, and start building. You mentioned earlier, like a human body, bones, skin, organs. A building is similar, right? Let's unpack the main physical parts, the stuff that gives it shape, strength, and makes it work.
Absolutely. Just like your feet support your entire body, a building needs incredibly strong foundations to stand firm, to stop it sinking or shifting. This crucial first step involves building excavations, basically, digging big holes or trenches deep into the ground. These massive foundations then do the vital job of transferring the building's enormous weight safely and evenly down into the earth below. It's often unseen, buried underground, but it's absolutely critical. Without solid foundations, nothing else really matters.
Okay, but I imagine some ground isn't always strong enough, especially for a really tall, heavy building like a skyscraper. What do they do then?
That's exactly when engineers need more advanced techniques. They use something called piles. Think of them like very long, thin, super strong legs that are pushed or drilled deep into the earth, sometimes hundreds of feet down.
Wow.
Until they reach a much stronger layer, solid soil, or even bedrock. And there are different ways to install them, depending on the ground. Some piles are driven in with a giant hammer, bang, bang, bang.
It's be noisy.
Very. Others are bored, where a large drill makes a hole that's then filled with concrete and steel reinforcement. Quieter, but maybe slower. Or even screwed in like a giant corkscrew twisting down into the ground.
How do they choose? Is it obvious?
Not at all obvious. It's a critical engineering decision based on many factors. The soil type, clay, sand, rock. How deep is the solid ground? Is there groundwater? How heavy is the building? Even noise restrictions in the area matter. Driven piles are fast but noisy. Board piles are quieter but might take longer. It's a complex calculation every time to ensure stability safely and efficiently.
Okay, so they get these super strong legs in place, but what about water? Basements can get damp, right? How do they stop water getting in down there?
Critical issue, especially with high groundwater. They use a technique called tanking. This isn't just paint. It's applying special, durable waterproofing layers to create a continuous, completely sealed barrier around the entire basement structure. The key word is continuous. No breaks, no gaps. And it has to extend above ground level, usually at least 30 centimeters.
Why above ground?
To stop moisture bridging, finding a path over the barrier and seeping down. It's effectively creating a perfectly sealed, waterproof box underground, protecting everything inside from damp and water damage.
Okay, foundations are in, waterproofed. Now it's time for the bones and skin of the building, right? The walls, floors, and roofs that enclose the space, make the rooms, and protect us from the weather.
Exactly. Walls are fundamental, and they can be made from a huge variety of materials, each chosen for specific properties. You see traditional natural stone, classic bricks, modern reinforced concrete, or even lighter, energy-efficient things like aerated concrete blocks. Each has different strengths. Some are great at bearing heavy loads from above. Others excel at thermal insulation, keeping heat in or out. Some are better for blocking noise. And besides holding the building up, walls resist forces from the ground, especially in basements. And of course, they divide the internal spaces, creating rooms and privacy.
And floors, they're not just flat surfaces we walk on, are they? They're constructed layers, floor slabs.
Yeah.
I remember being in an old apartment once. You could hear everything from upstairs, every footstep. Bet they needed a floor refurbishment.
That's a perfect example. Sometimes, especially in older buildings, these floor slabs absolutely need refurbishment. To improve things like sound insulation, exactly your point. Or maybe upgrade fire resistance for safety. It might involve adding new layers, special insulation, maybe even replacing sections. And floors aren't just functional. Architects can use beautiful materials. The sources mention mosaic flooring, small pieces of stone, glass, or ceramic arranged in intricate patterns.
Oh, like an old Roman villas.
Exactly.
Yeah.
Tiny squares, hexagons, creating stunning designs right on the floor, turning a functional surface into art. It's a lovely blend of engineering and artistry.
That mosaic idea is beautiful, shows the detail. Now, the roof, the building's hat, protecting us from rain, sun, wind, more complex than just a lid, I assume.
Absolutely, it's the primary shield. Broadly, two main types. Pitched roofs, sloping, like a traditional house, great for shedding rain and snow. And flat roofs, which look flat but have a slight incline for drainage. For pitched roofs, the angle of the slope is critical. It affects material choices, how water runs off. And they have to prevent condensation inside the roof structure. Warm, moist air from inside hits colder surfaces in the roof, water forms, leading to damp, mold, damage.
How do they stop that?
Often with a vapor barrier, a special impermeable layer on the warm side of the insulation. It stops that moist air getting into the roof layers in the first place. A silent guardian.
Clever. But what's really fascinating to me is this idea of green roofs, flat roofs covered with plants and soil. That sounds amazing.
They are amazing, not just for looks. They have incredible benefits. They help cool the building naturally, insulation plus plant transpiration. They absorb huge amounts of rainwater, reducing strain on city drains, preventing flooding. They even reduce noise pollution.
Imagine if all buildings had gardens on top, like giving cities a giant natural air conditioner, better air, more biodiversity, just nicer places to be. But it must be complex to build, heavy.
That's the challenge, yes. The biggest one is the weight. Soil and plants, especially wet, are heavy. The roof structure has to be designed specifically to bear that extra load. Drainage is also critical. You need sophisticated layers to manage water enough for plants, but no waterlogging. And the waterproofing underneath, absolutely crucial. A leak under a green roof is a nightmare to fix. Plus, plants need maintenance. So it's a complex interplay of structure, landscape design, waterproofing. But the long-term benefits often make it worthwhile.
Okay, let's talk about the building's eyes and mouth, windows and doors. They're way more than just holes in the wall, right? They connect us, protect us, affect comfort, energy.
You're absolutely right. Windows are complex systems. Yes, they let in light, give us views, but critically, they keep out heat or cold, block noise. That's why we have thermally insulating double-glazed units, 2 panes of glass, sealed gap between, sometimes filled with inert gas like argon.
Why the gas?
The trapped gas is a fantastic insulator, drastically reduces heat transfer, saves huge amounts of energy on heating and cooling. There's even low-E glazing, a microscopic invisible coating on the glass. Reduces heat transfer even more, but still lets lots of light through. It's clever material science.
Brilliant. A tiny gap, an invisible coat, big difference. And doors, also complex. Access, security, flow.
Indeed. Doors are fundamental. So many types. Simple, single-leaf doors like your bedroom door. Grand revolving doors in lobbies, they minimize drafts, act like an airlock. Sliding doors save floor space. But beyond just opening, security is huge. In large buildings, offices, apartments, maybe central locking systems, one master key for many doors, even more advanced, electronic access control, using a card, a fingerprint, a PIN instead of a physical key.
Like hotel key cards.
Exactly. Incredibly practical. Easy to assign or remove access instantly. Someone checks out, card deactivated, employee leaves, access removed. No need to change physical locks constantly. Huge benefit for security and management.
Makes total sense. Now, this raises a question. How do people move inside these buildings? Especially big ones, vertically, horizontally.
Good question. For vertical movement, mainly three things. Stairs, escalators, and lifts, or elevators, as many call them. Stairs need careful design, not just safe, but comfortable. Specific riser, step height, and tread depth dimensions.
You know, some stairs just feel right to climb.
That's good design. Ergonomic proportions for the human stride. Then for buildings with many floors, escalators and lifts are essential. Escalators move lots of people steadily. Lifts are critical for accessibility and speed to higher floors, making tall buildings usable for everyone.
And lifts in really tall buildings can be super fast. How do they manage crowds, like in airports or big office towers?
That's advanced engineering. Lifts can be incredibly sophisticated, especially in high-rises. Some use destination floor control systems. This is really clever. Instead of just pressing up or down, you enter your destination floor before you get in, maybe at a lobby terminal. The system tells you which specific lift car to take. It groups passengers going to similar floors, minimizes stops, speeds up travel time hugely, especially at peak times.
Wow, that's smart.
It really is. They can even integrate security card readers, biometrics allowing access only to certain floors or people. Enhances safety and control significantly. Intelligent building systems at work.
Okay, this is fascinating, getting into the guts of the building. Now let's step back a bit. Just like people have different needs, a student, a family, a patient, buildings have totally different purposes. A home is so different from a school, which is completely different from a hospital. Architects and engineers don't just build generic boxes, they design each space specifically for you and what you'll be doing there. Let's explore how they tailor these spaces. Right, your home, probably the most personal space you have. And every part of it, from countertop height to doorway width, is designed with daily life in mind, even if we don't notice.
Absolutely. And when designing homes, architects think a lot about accessibility. Not just for wheelchairs, but for everyone. Young kids, older people, someone carrying a heavy box. For example, door thresholds, that little bump at the bottom of the door frame, ideally avoided completely, or if needed, no higher than 2 centimeters.
Why so specific?
Prevents tripping hazards. Makes it effortless for strollers, wheelchairs. Just seamless movement for everyone. It's thoughtful, inclusive design.
Such a simple detail, huge impact. Okay, think about your kitchen. Why is it laid out like it is? Sink near the stove. That amount of counter space.
Well, there's a logic. Engineers calculate the best spots, often following the kitchen triangle idea, minimizing steps between sink, stove, fridge for efficiency. And they focus on enough worktop space, counter space, right next to key appliances like the stove and sink. For safety and workflow. Like the sources suggest, a small worktop between cooker and sink should be at least 50 centimeters wide. For prep, setting down hot pans, a larger main worktop, maybe 120 centimeters. It's all about creating an intuitive, functional, safe space for cooking without feeling cramped.
A finely tuned cooking machine. And it's not just kitchens, is it? Bedroom sizes, wardrobes, they seem standardized too?
They are. And for good reason. Bedroom sizes aren't arbitrary rectangles. A comfy single room. Recommended minimum 16 square meters. Enough space for bed, desk, wardrobe moving around. Rooms for 2 or 3 beds, maybe 8 square meters per bed. Balancing personal space and utility. And wardrobes. Designed with incredible detail. Specific dimensions for hanging suits, long coats, shelves for shoes, folded items. They consider how many things a person might own.
That's detailed. And storage space, always crucial, but easily forgotten until you run out. Architects plan for that too.
They certainly do. Storage is a hidden hero. Sources recommend about 1 square meter of dedicated storage inside a flat, separate from bedroom closets. For larger homes, maybe 2% of the total floor area. For personal items, cleaning supplies, keeping living spaces uncluttered, often practical to put some near the kitchen. And a clever detail, storage room doors often open outwards.
Oh, why?
Saves space inside the storage room. Lets you maximize shelving right up to the door frame. It's all about practical, livable design.
Okay, moving from home to school. Your school isn't just a building with classrooms, it's like a giant learning machine. Every part designed to help you learn, interact, grow safely.
Absolutely. For education spaces, especially science, architects calculate space per student very carefully. Regular classroom teaching, maybe 2.5 square meters per student. But for lectures, science demos, where you need room for experiments, viewing, it goes up to maybe 4.5 square meters per place. Accounts for equipment, safety clearances, students moving around, observing. It's pedagogy meets spatial planning.
Makes sense for labs. What about playgrounds? I always thought they were just, a patch of grass designed to.
Definitely not just a patch of grass. Playgrounds are vital. For housing, there's often a requirement 5 square meters of play area per home. Minimum total area, maybe 40 square meters. Ensures kids have a dedicated, safe, stimulating space. Crucially, they need fencing, minimum 1 meter high. Keep kids safe from roads, dangers like water. Plus, they consider surfacing soft landing materials, shade, age-appropriate equipment. It's about creating a secure, enriching environment, not an afterthought.
Wow, playground design. Okay, more specialized learning university laboratories. This must be super specific.
Incredibly specific and very hugely by discipline. Chemistry, biology labs. Often need lots of fume cupboards, ventilated enclosures, pulling away dangerous gases. They require very high rates of air exchange. Safety first. Physics labs. Maybe mobile benches for different setups. Less need for extreme air exchange, but require much more sophisticated electrical setups, power outlets, grounding for sensitive equipment. Each lab is a unique puzzle, balancing safety, function, flexibility for its specific science.
So next time you're in a science lab, maybe notice the special ventilation, the bench layout, the flooring. It's all planned for safety, efficiency, and optimizing learning. A silent partner in education. From classrooms to clinics, hospitals, these are incredibly complex buildings, way more intricate than homes or schools. Designed for peak efficiency, strict hygiene, critical safety, health is on the line.
Absolutely correct. Preventing infection spread is paramount. Life-threateningly important. This means designing very specific routing systems, separating different traffic functions, keeping clean areas, sterile equipment, meds, food totally separate from dirty areas, waste, soiled linens, patient flow separate from staff work areas. Public access controlled. A common strategy is a 2-corridor system, physically separating patient staff or clean dirty goods. Minimizes cross-contamination, enhances safety hugely.
Brilliant logic to minimize risk. What about patient rooms? Must be meticulously designed too, for patient comfort and staff efficiency.
Precisely. Huge attention to detail. Patient beds accessible from at least 3 sides. So doctors, nurses can easily attend from any angle, use equipment without awkward maneuvering. Usually a table by the window for meals, personal items, sense of normalcy. Size matters too. Single room, typically at least 16 square meters. Allows movement for patients, staff, equipment, ensures privacy. Multi-patient rooms, about 8 square meters per bed. Adequate personal space, but still allowing staff easy access, quick response. It's comfort, plus highly efficient care delivery.
Okay, from healing spaces to bustling public hubs. Ever notice how easy it is to navigate a huge shop? Or how clear the signs are at a busy bus stop or train station? Not an accident. These places are designed with amazing precision to manage crowds, guide movement, keep you safe, often without you even realizing the choreography.
Retail spaces, supermarkets, malls meticulously designed to guide your journey. Subtly encouraging exploration, checkout areas, laid out for maximum efficiency, speed. A single cash desk, maybe 1.70 meters wide. An island cash desk, a supermarket with a big packing area, could be 1.30 meters wide. Faster processing, more bagging space. Even emergency corridors for customers have rules at least 2 meters wide. Safe evacuation, no bottlenecks. Every aisle display, counterpart of a plan for experience and safety.
Even the checkout line engineered. And public transport, bus, train, metro, every detail planned for flow, speed, safety on a massive scale.
Absolutely. Take bus stations. Engineers calculate exact parking spaces needed. Standard bus space, 3.5 meters wide for maneuvering. Arrival lane width, typically 4.0 meters. Smooth entry-exit, avoid bottlenecks, keep things punctual. It's a logistical puzzle.
Railway stations must be even more complex. Thousands of people, massive trains.
Indeed. Incredibly specific requirements for platforms, stairs, Managing crowds safely. Fixed stairs, which should be a multiple of 0.60 meters, minimum 2.40 meters overall. Accommodates flow, avoids bottlenecks, handrails both sides. If stairs are very wide, 6 meters, extra handrails down the middle. Even clearance profiles, the minimum space around tracks, defined down to centimeters. To keep buildings, platforms, people safely away from moving trains, prevents awful accidents. It's an intricate dance, human movement, massive machinery.
And then airports, miniature cities really, serving millions yearly. Everything, runway system, number, layout, the terminal, check-in, security, gates, the apron where planes park, refuel, load. Designed to handle millions of passengers, huge aircraft, safely and efficiently. It's a monumental logistical puzzle. How do they even start planning that?
Planning an airport is a massive challenge. Starts with forecasting passenger numbers, aircraft types, decades ahead. Then design the runway system, minimizing weights, maximizing safety, considering winds, simultaneous operations. The terminal is designed around passenger flow drop-off, check-in, security, gates, baggage claim, intuitive paths, minimizing congestion, stress. The apron, laid out like a giant, precise parking lot for planes, safety distances, refueling, ground support. They even factor in future expansion. It's integrated design on a huge scale, a constantly moving ecosystem.
Wow. We've gone from city planning down to kitchen counters. We've seen the outside, explored the inside, understood the human focus. But what about the hidden magic? The invisible systems making buildings comfortable, efficient, safe, working silently behind the scenes, building services, infrastructure.
Exactly. Like your body's circulatory system, buildings have intricate supply and disposal systems. They're lifeblood. Networks of pipes bring clean water supply, drinking, bathing, washing. Lines deliver gas supply, heating, cooking. Intricate wires for electricity, powering everything from lights to laptops. These are the hidden backbone, quietly ensuring our daily needs are met, often without a second thought.
Perfect analogy. Vital organs working nonstop. And waste. Not glamorous, but essential for a healthy building.
Absolutely crucial for hygiene. Multi-story buildings might have rubbish chute systems, quick, hygienic disposal to a central point. All buildings need designated rubbish collection rooms at ground level, designed for efficient sorting, storage, properly ventilated, easily accessible for collection trucks. Goal is safe storage, easy collection, no odors, no pests, maintaining cleanliness and public health, fundamental part of urban life.
Ever walked into a room and thought, oh, this feels right. Not too hot, cold, noisy, perfectly lit. That's not luck. That's smart engineering, smart design, working silently for your comfort.
Thermal insulation's a prime example. How easily heat moves through walls, windows, roofs. Think of your winter jacket. A good one has a low U value that measures how easily heat passes through. Low U value means little heat escapes, keeps you warm. Thin t-shirt, high U value, heat passes right through.
Got it. Low U value is good insulation.
Exactly. Engineers aim for low U values in building materials. Keeps buildings cool in summer, less heat gets in, warm in winter, less heat escapes. Directly means lower energy bills for heating, cooling, more sustainable, more comfortable year-round.
Makes perfect sense. And energy isn't just about insulation. Modern buildings use renewable energy now, right?
Absolutely. Sustainability is transforming design. First, solar energy, specifically photovoltaics, those solar panels on roofs. Amazing. Converts sunlight directly into electricity, clean, emission-free. But placement is key. Need to avoid shadows, which kill efficiency. Then bioenergy, using organic stuff like wood pellets from waste, burned for heat like an oil system, but sustainable. And geothermal energy, this is super cool. Taps into the Earth's constant temperature a few meters down.
The ground's temperature.
Yeah, it stays fairly stable year-round, maybe 7-11 degrees Celsius. Use it for heating in winter, cooling in summer. The ground acts like a giant natural battery. Incredibly efficient climate control.
Mind-blowing. Using the Earth itself. Now lighting. More than just switching on a bulb, isn't it? The way light falls changes everything.
Completely. Lighting is critical for comfort, mood, function. Designers consider different types. Direct lighting shines straight down. Good for tasks like kitchens, offices. Indirect lighting bounces off ceilings or walls first. Creates softer, diffused light, less glare, fewer harsh shadows. Often used in living rooms, galleries. Careful placement highlights features. Creates atmosphere. A subtle art and science.
And sound. Can't imagine learning in a noisy classroom or relaxing at home hearing everything outside. Sound insulation must be vital.
Vital for peace and well-being. Reducing unwanted noise traffic, neighbors, machinery. Sound travels as vibrations, pressure waves, measured decibels, dB. Loud chat, maybe 60 dB. Architects design walls, floors, windows to block sound, airborne sound conversations, music, and structure-borne sound vibrations from footsteps, washing machines traveling through the building itself. It's complex. Careful material selection, construction techniques create peaceful spaces, which leads to room acoustics, how sound behaves inside a space. Ever been in an empty hall? Echoes everywhere. Or a good concert hall. Sound is clear, rich.
Yeah, big difference.
That's reverberation time, how long sound lingers. Architects avoid parallel flat surfaces in auditoriums. They cause flutter echoes, sound bouncing back and forth like ping pong. Make speech unclear, music muddy. They shape walls, ceilings, use absorbent materials to guide sound evenly, ensure clarity for speech, richness for music, making sound perform beautifully.
Finally, beyond comfort, efficiency, design. Buildings have amazing built-in safety features, working invisibly to protect us from serious dangers. Fire, lightning.
Fire protection is paramount. Life and death. A key element, fire compartment walls. Special walls, fireproof, structurally stable for a set time like F90A. 90 minutes, non-combustible materials. They act like barriers, stop fire spreading, contain the blaze, often run from foundations right up above the roof. Creates isolated zones, buys precious time for evacuation for firefighters, prevents total loss, saves lives.
Incredible engineering, those fireproof zones. And sprinkler systems, like in movies, but real.
Very real, incredibly effective. A building's own automatic fire brigade, network of pipes, special sprinkler heads. If a head detects fire heat, it activates automatically. Sprays water onto the flames, extinguishes or contains the fire until firefighters arrive. Hugely effective at protecting lives, property, often stops fires before they spread much,
Right.
drastically reduces damage, ensures safer escape.
Lightning, so powerful, unpredictable. How do buildings handle that?
Another crucial safety feature, especially for tall buildings, lightning protection systems. Use roof conductors, metal rods, or lines on high points, and earthing rods deep in the ground, designed to capture a lightning strike, that massive electrical discharge, and guide it safely into the earth, bypassing the building structure, protecting everyone inside.
Like being in a car during a storm.
Exactly the principle. The car's metal body is a Faraday cage. Electricity flows around the outside into the ground. You're safe inside. A building lightning protection system does the same. Creates a safe path for that immense current around the building into the earth. Keeps you perfectly safe within. #Notro.
Wow, okay, we have covered a lot today. From tiny details like a door hinge up to the massive scale of an airport, it's so clear our built world isn't just there. It's meticulously planned, ingeniously engineered, and thoughtfully designed with you, the person using it, very much in mind.
Indeed. We've peeled back the curtain today, haven't we? Seeing how human psychology influences the dimensions of our spaces, how materials are chosen for beauty and safety, how invisible systems keep us comfortable, protected. Every single choice, the slant of a wall, the type of window glass, it's all part of a grander vision, creating environments that serve us optimally, efficiently, safely.
So what does this all mean for you listening right now? Well, it means you now have a new superpower. The ability to see the hidden magic, the incredible intelligence baked into every building you encounter. You can walk through your school, your home, a shop, a hospital, and start to understand why things are the way they are. The thought process behind it all. The problems designers were solving for us.
Which really raises an important question, doesn't it? Now that you know these secrets, these underlying principles, how will you look at the buildings around you differently? Will you start noticing the flow, the light, the safety features, maybe even those subtle psychological cues shaping your experience?
Yeah. Next time you walk into any building, anywhere in the world, what new secrets will you notice? Things you never saw before. Will you think about the human measurements that shaped the stairs, the sound insulation keeping out the city noise, the hidden pipes bringing water to your tap? The world, its built form, is now like an open book of design, just waiting for your next deep dive.